Okay, so for Calc 1 today, we're going to go over one of the harder sections in the book. We're going to go over optimization. If you were in the last meeting, I may have already previewed some of this with you. So we're going to kind of make a video for those people that weren't there, and also I'm going to continue on with some more problems. So the main thing for optimization is we're trying to find a way to use derivatives to help us figure out how to optimize or how to solve problems with optimization. And optimization could be something such as minimizing cost or maximizing revenue or maximizing, you could maximize area, maximize volume, minimize distance. You know, that's what optimization means for us, is finding ways to minimize and maximize things that we care about. So for our class, we're going to use these guidelines that I have written in front of you to help us with optimization problems, okay? So first thing you gotta remember is every problem is gonna be different, so you gotta read it carefully and make sure you understand what they're saying or what they're asking for, okay? If you can, the second thing you should do is draw a picture. You can't always do this, but you give it your best shot if it's something that seems very realistic or very easy to draw. Determine the functions needed. Usually for our class, it'll be 2. It doesn't have to be, but usually it will be 2. And then we write the quantity that you are trying to optimize in terms of one variable. So our goal is to take these 2 equations and use them to write one equation, okay? With only one variable, I'm sorry, to take them and use the 2 equations to write an equation with only one variable. Take the derivative of that function and determine the critical numbers and do a sine chart. So basically what we've been doing in the previous sections, we're gonna now use on optimization. Take the derivative of the function, determine critical numbers, and do a sine chart. Then we're going to check the endpoints as well, if necessary. Sometimes the endpoints don't make sense to check them. They're something that wouldn't make sense in the problem. And then make sure you have answered the question. So from our sine chart, we should be able to identify min, or let's say maxes, so once we do a sine chart, we should be able to identify mins or maxes, okay? And then from there, we should use those values to create either a maximum value or a minimum value, which will help us optimize the problem. And then the final thing, make sure you've actually answered the question that they were looking for. Sometimes people answer the wrong question and they did all this really good work for nothing, okay? So it says, first problem we're gonna work with, and we're gonna try to use these guidelines. Find 2 numbers whose difference is 100 and whose product is a minimum, okay? So we're gonna come up here, and every problem is different, read it carefully. So we're talking about 2 numbers. They don't say whether it's positive or whether it's negative, they just say 2 numbers, and they say their difference is 100. So I'm gonna write one of my equations. I'm gonna call x minus y equals 100. So that's 2 numbers whose difference is 100. I'm going to come over here, draw a picture. That doesn't really make sense to do. Determine functions needed. I got one function so far, x minus y is equal to 100. And then it says, and whose product is a minimum. So the function that I'm trying to optimize is the product. So I'm just going to say product is equal, and you could even write out product if you wanted. In fact, I'll do that. So product equals x times y, and we want minimum product. Okay. I'm going to eventually switch to the letter P for product, okay? So according to my guidelines, we got our 2 functions, okay? So we have P equals x times y, and we have x minus y equals 100. So I'm gonna solve for one of these variables. It looks like to me x is the easiest to solve for. So I'm going to come over here and I'm going to say x equals 100 plus y. Okay, so I now have x equals, and I'm going to use that to plug into that x equation. Maybe I should use green. Okay, so we're going to come over here and I'm going to say p equals 100 plus y times y. But that's really 100y plus y squared. Okay, so now we're going to go, let me pause real quick. Okay. Sorry about that, you guys. My dogs were barking. I was going to try to go yell at them, but they stopped. Sorry about that. So we have 100y plus y squared. Okay. And this allows us to have only one variable. So we've done our job. And it says, write the quantity you are trying to optimize in terms of one variable. So we have P equals 100y plus y squared. So that's one variable. Okay. So now step 5 says, take the derivative of that function and determine the critical numbers and do a sine chart. So what I'm going to do is I'm going to find P prime, and that's going to equal 100 plus 2y. Okay. So I could factor this, and this would be 2 times y plus 50. So if I want to do a sine chart, I need to find my critical numbers. Okay. So let's do over here, y plus 50 equals 0. So y equals negative 50. So I'm going to put negative 50 on my sine chart. And now I'm going to test, this is P prime. I'm going to test, or dp dy, whatever way you want to say it. So I'm going to test negative 50 to the left in my derivative. So negative 50 to the left, or to the left of negative 50 would be, let's say, negative 60. And if I plug negative 60 into here, I would get negative 60 plus 50 would be negative. So I know that I'm going to get negative. Okay. And then if I plug, let's say, negative 40 in to here, I know that I'm going to get negative 40 plus 50 is 10, so that's positive. So I know I'm going to get positive. So again, what we're finding here is we're finding that we're getting a decreasing to increasing. What does that symbolize to us? That symbolizes a minimum or a local min. So now we come over here and we say y equals negative 50 is our local, or is a minimum, could be a absolute min, but is a minimum. Okay. Now what we're going to say is we need to find x, and we know x is equal to, we solved it right here, right? X is equal to 100 plus y, but y is negative 50. So then x equals 50. Okay. So we now know that x equals 50. We know that y equals negative 50. These are the two numbers that when you multiply them together, they will give you the minimum product, okay? When you find the difference of 50 minus a minus 50, you do get 100, and they ask you to find the minimum product. So P equals negative 50 times 50, and we get negative 2,500, okay? So our minimum product is negative 2,500 as well. So we also found that. Okay, so we found the x, the first number or the second number, we found the first number, and we found the minimum product, so we're good. Okay. So I think in the homework you guys will see quite a few of these. I think there's 2 or 3 minimum of these, so make sure you take a look at this problem and go through that. So I have another problem involving a rectangle, and it says find the dimensions of a rectangle with an area equal to 100 meters squared whose perimeter is as small as possible. Okay. So once again, our guidelines say read the problem carefully. So what are we trying to minimize? We are trying to minimize, once again, perimeter. So we know perimeter is equal to 2 L's plus 2 W's. Okay. And then we need to discover what is our other equation. Normally we need 2. Well, it says the dimensions of a rectangle with an area equal to 100. So we know that area equals length times width. Okay. So we have 100 equals L times W. Let me write that a little bit nicer. Okay, so now these are our 2 equations. We're ready to go. Now let's solve for, I don't know, let's solve for L just because. So I'm going to solve for L. I could just as easily solve for W. So I'm going to divide both sides by W, and that's going to give me 100 over W is equal to L. And you guys know that now I can take this and substitute it in. Remember, we're doing now the 4th step, write the quantity you are trying to optimize in terms of one variable. So I'm doing step 4, or guideline number 4. So I'm trying to write this in terms of one variable. So this is going to become perimeter is equal to 2 times L, but L is 100 over W plus 2W. So let me just clean this up a little bit. So this will be 200 over W. You know what? I'm going to write this as 200 W to the negative 1 plus 2W because I know I'm going to have to differentiate this problem, so I'd rather have it as a negative exponent. Okay, so now we're going to find P prime is equal to negative 200 W to the negative 2 plus 2. So we have now found our derivative. This is step 5. Right, guideline 5 says take the derivative of that function and determine the critical numbers and do a sign chart. So let's go up here. Let's find our critical numbers. So we are going to be left with P prime equals negative 200 over W squared plus 2. Okay, so normally when you're trying to find critical numbers, you don't want to have a two separate fractions. You want one. So this is going to be negative 200 plus 2W squared all over W squared. So all I did was make them have common denominators. Okay, so now we have P prime is equal to 2W squared minus 200 over W squared. Okay, now we have to find our critical numbers. Now I don't really have to set the denominator equal to 0. Think about it. If the denominator is equal to 0, that is a potential critical number. However, can a rectangle have a width of 0? Can a rectangle have a width of 0? So that's more of an endpoint. That is not really a possibility for my width. It's not really in the domain of the story. So I'm only going to mess with the 2W squared minus 200. I'm going to set that equal to 0. But that's really 2 times W squared minus 100. And I'm going to set that equal to 0. And then this means 2W minus 10 and W plus 10, difference of squares. So then I'm left with W equals 10 or W equals negative 10. Well, we know that we can't have a negative width, so we're going to throw that one out, right? So then we know that W equals 10 is going to be our critical number. Okay, so this is our critical number. And we're going to put 10 right there. So I'm going to test to the left of 10. That would be 9. So if I put 9 into here and 9 into here, I would get, let's see, a negative 1 and a positive 19. So that would be negative. And then if I go back and do the same thing, but this time I put an 11 in here and an 11 in there, that'll be a positive 1 times 21. So that'll be a positive. So notice we're going from decreasing to increasing. So we have a local min. So we know that W equals 10 and causes a local minimum or a minimum. And we know that L is worth 100 over W, but W is 10. So L is worth 10. So as it turns out, W equals 10, L equals 10, okay? Oops, I did kind of mess up. I forgot to draw a picture. Sorry, guys. This would have been a really good problem to draw a picture. Sorry about that. That should have been something I drew in the very beginning. I got carried away. Now, it looks like a rectangle, but in reality, after discovering this, we know that it's actually a square. So in this case, a square is the best way to minimize perimeter. Okay, and what is the minimum perimeter? Equal, what, 10, 10, 10, and 10, so that would be 40, okay? 40 meters. Okay, so the smallest possible perimeter you could ever make would be 40 with any rectangle that has a width of, or that has an area of 100. And you could try to figure out if you could find a better one. You could say, well, what if I use a width of 20 and a height of 5 or a length of 5? Well, that'd be 100. However, that would also be 50 as a perimeter, so not smaller than our 40. So what we're saying is the smallest perimeter you could ever make with a rectangle that has an area of 100 is a perimeter of 40, and that would be a square, okay? So hopefully you guys are okay on that. Now, if you guys could pause the video, read this next question, Find the point on the graph y equals x squared plus 1 that is closest to the point 0, 2. So you guys should pause the video and see how far you could set this up before you hit a roadblock, okay? So I would say definitely for this problem, draw a picture first. That should be the first thing you do, and then label what they're saying, okay? So pause the video and kind of get started, and then unpause it to see where I ended up. Okay, you guys, so you're coming back from the pause. Hopefully you drew this picture over here, right? And this is a parabola, y equals x squared plus 1. This is a parabola that is shifted up 1, right? So I'm just going to put it right here. Well, you guys get the idea. That's not an ideal parabola, but you guys get the idea. All right. And they say find the point on the graph of y equals x squared. So there's some point on the graph, let's say right here. And then it's going to be closest to the point 0, 2. So we have our point 0, 2, which is right about there. So that's our point 0, 2. Okay. Now, here's the thing. They want to know the point on the graph that is closest to that point. So I need to come up with a name for this point. I'm going to call it x comma y. And again, naming points something kind of helps in calculations, because if you want to use formulas and stuff, you have to know what you're using, what you're plugging in. So in this case, whenever we want to talk about this point P right here, if we ever want to talk about that point, we're going to use an x and we're going to use a y, which makes sense, okay? Something simple like naming the point can really help the problem come together. And then we have our other point here, which I wrote too small. So this point here is 0, 2, okay? Now, we drew our picture, and what we're trying to find is this distance from here to be a minimum. So that should tell you right there what we're trying to minimize. We are trying to minimize distance, okay? So I'm going to write the distance formula, okay? So hopefully you guys all remember the distance formula is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And in reality, you could do x1 minus x2 squared and y1 minus y2 squared. Because you're squaring it, it's going to work out fine. Okay, so normally we need two equations, okay? But I'm just going to try to plug in what I know for this distance formula. By the way, if you took me for pre-calc, we did a problem similar to this, but we used the calculator to find that minimum, okay? Where we graphed it and then found that minimum on our calculator, and that was our local min and max section. We graphed the distance formula. So here we have d is equal to the square root. Now I'm going to plug in the points. So I'm going to say my x2 is x and my x1 is 0 squared, plus my y2 is y and my y1 is 2 squared. So then this is going to equal the square root of x squared plus y squared minus 4y plus 4. Excuse me. Okay, so x squared. So now normally we would like to have a problem that only has one variable in it, but we have two. We have a y squared and we have an x squared and we have a y. So we have two variables. However, if you look up here, in the highlight, you see that y is worth an x squared plus 1. So this is actually our second equation. They gave it to us already. We don't have to go and write it. They gave it to us. So I'm going to plug in for y. So this is x squared plus 1 squared minus 4y. Oops, but y is actually x squared plus 1 plus 4. So now let's do a little more cleanup. So this will be x squared plus x to the 4th plus 2x squared plus 1 minus 4x squared minus 4 plus 4. Okay, and let's just keep cleaning. So now this combined like terms will be x to the 4th. Let's see, if we add all these up, we should get minus x squared. And then these two cancel, and I think it's plus 1. I think all we get is plus 1. Let me double check to make sure I'm on the right path. Sure. Okay, so now we have that. Now the nice thing about distances is the minimum distance would also be the same if we squared both sides. So I'm going to say let's square both sides, and you'll see why I want to do this in a second. This would be d squared is equal to x to the fourth minus x squared plus 1. So I'm going to rename this d squared some new distance. Let's call it d hat. And that would be x to the fourth minus x squared plus 1. And what we're doing here is we don't want to have to mess with a big nasty derivative. You guys could go through right here. You guys could go through and do the derivative of the original of this problem here. Before I square rooted it, you could go and do that derivative. And you would get the same minimum or maximum that I would get from doing d squared. So this new d hat is basically a way around having to deal with the square root and the chain rule, okay? And it'll still give us the same mint. So we're going to now do d hat prime. D hat prime is equal to 4x cubed minus 2x plus 1. And again, you guys, all I'm doing is I'm going through these guidelines. Draw the picture if possible. We did it. Determine the functions if needed. We did that. Write the quantity you are trying to optimize in terms of one variable. The distance formula we just wrote in terms of one variable. We take the derivative of that function and determine the critical numbers and do a sine chart. So that's where we're at now. So let's do our little sine chart over here. So we need to find this derivative. So I'm going to come over here. I'm going to set this equal to 0. 4x cubed minus 2x plus 1 equals 0. Let me see here. We could factor a little bit, it looks like. Oh, wait, I think I might have. Oh, yeah, I messed up. So let's go back here. The derivative of this does not have a plus 1, right? So please erase that plus 1. The derivative of plus 1 is 0. So we're going to set 4x cubed minus 2x equal to 0, but that's really 2x times 2x squared minus 1 equals 0. So then we have x equals 0, and we have x squared equals positive 1/2. I just took this and I set it equal to 0. Now we square root both sides, and we get a plus or minus. So now we have x equals plus or minus the square root of 1/2. And why am I not going to use 0? Why am I going to say this one doesn't really count for us? Well, you can't really have a distance equal to 0, okay? You know what? It's not the distance because that's the x coordinate. We still have to actually use it. So I'm going to put the 0 here. I'm going to put the square root of 1/2 here. And I'm going to put the square root negative 1/2 here, okay? Yeah, we actually do have to use all of these because the x coordinate could actually be 0. That's my fault. Okay, so now we're going to do a sine chart. So you guys can plug these in your calculators as decimals. So I'm going to test to the left of negative square root 1/2. And if you do, you plug in, you get negative. By the way, this is d hat prime. This is the derivative. And when you plug in something between 0 and negative 1/2, you should get a plus, 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 plus. When you plug something in between 0 and 1/2 into d hat prime, you should get a minus, minus, minus right here. And then again, you should get a plus, plus, plus right here, okay? So once again, we're going this way, to this way, to this way, to this way, okay? So what are we concerned with? We're only concerned with local minimums, not local maximums. So I see that I have a local min here and I have a local min here because I'm going from decreasing to increasing, okay? So that means that x equals negative, x equals negative square root 1/2, x equals square root 1/2. These are my two x coordinates, but it says find the point on the graph. Well, that means I have to plug x in to y equals x squared plus 1. So y equals x squared. So this is negative 1/2. You know what? I'll just do the positive one. Because when you square it, you're going to get positive anyway, plus 1. So that would actually turn out to be 1/2 plus 1, which is actually 3/2. So we now have found our 2 points. We have now found that you could use negative square root 1/2, comma 3/2, and you also have square root 1/2 over 3/2. These are both the correct points that would minimize the distance. Now think about it. Why are there 2 points? Well, because it's a parabola and it's symmetric. So whatever guy that I drew right here, whatever line, there has to be a matching one over here, right? And that's what we just found. We just found our 2 points, negative square root 1/2, comma 3/2, and square root 1/2, comma 3/2. Okay, so those are our 2 points that would minimize the distance. They are the closest to the point 0, 2 on the parabola. You know, we're saying not here, not here, not here, not here, not here, not here, not anywhere else besides those points. Those 2 points would be the closest that you could ever do to minimize this distance, okay? So hopefully you guys got quite a ways in that one. So take a look at this one. Now again, you're trying to do this without my help. So pause the video once again, and it says a flat sheet of cardboard that is 16 inches by 21 inches is used to create an open box by cutting 4 squares out of the corners of the sheet of cardboard. Find the size of the square that will yield a maximum volume. So they want to know what size do you need to cut out of those corners in order to make the biggest box you can, that can hold the most volume, I should say. Okay, now they're giving you a flat sheet of cardboard, and they're trying to find a way to maximize this volume that this piece of cardboard can make. Now it doesn't have a lid, okay? So kind of think of it almost like an empty shoebox. You're trying to create an empty shoebox without a lid on it, okay? So pause the video, take a minute, try to set this up, draw your picture, see what it looks like, and then unpause it and we'll go over it together. All right, so you guys should be back from your pause. I'm gonna draw my shoebox, or I should say my sheet of cardboard. Okay, and we know that it is 16 inches by 21 inches, okay? And we also know that we're gonna cut these corners out. And they said they're squares, so even if mine don't look like squares, they are actually squares and they're all equal size. So now we need to label some stuff on this, okay? Do you know the size of the cut you're making? The answer is no, right? You don't know the size. So we're gonna name it something we don't know. Now here's the thing, if I know that dimension of the cut, I actually also know this dimension of the cut. You guys all know because they said it was a square. They said cutting out squares. So that's what allows us to make sure that we know that it's an X and X and X everywhere, okay? So what is the formula that we're trying to optimize? Well, we're trying to maximize volume. So what I'm gonna do is I'm gonna try to write the volume formula for a box, okay? So for a rectangular solid. Well, that turns out to be the easiest one. You may not have all of them memorized, but you should know that this is length times width times height, or base times width times height, however you learned it, okay? Or even times depth, or whatever you want to say, okay? So needless to say, this is our formula. And now we have to find a way to get rid of all of these variables, right? So we're trying to maximize volume. So the volume is going to stay because we're going to be left with V prime or dV d something, right? I think in this case, it'll be dV dx because X is the variable we're working with. So we're going to have V. So let's see what we can get for L. Well, L is the length, right? How far across this box is going to be. Well, normally we would say it's 21, right? However, look at the cut. You're cutting this length out. You know, you're cutting this length out and you're cutting this length out, right? That's not going to be there. Just like you're cutting this length out and you're cutting this length out. So those are not going to be there. So you're cutting out 2 X's. I don't know what distance that is, but I know I'm taking 2 of them away. So I'm going to minus 2 X's. Okay. Now let's do the width. Now you should be able to get the hang of it. Similar idea. We're now cutting this distance out right here, and we're cutting this distance out. We're cutting this distance out, and we're cutting this distance out. So you guys should be seeing that we're cutting a 2x from each dimension. Now, this is kind of the hard part to visualize, but if you folded these sides up, okay, what is the height of the box now? Well, the height of the box is however much you cut out, because it is, when you fold it, that's how much will be left hanging up. So X is actually your height. So now we have to FOIL this out, and I'll just give you guys a heads up. It's going to take you a minute. So I'm going to write it out for you. 336 X minus 74 X squared plus 4X cubed. It's just FOIL and then multiply by X, and you should be okay. All right. Now we need to take the derivative of both sides. So I'm going to ddx both sides. So we're going to get dv dx is equal to 336 minus, oops, that's what, 148 plus 12x squared. Okay. Now I don't normally like to write like this, so I'm going to rewrite it as 12x, I already wrote it down, 12x squared minus 148x plus 336 equals 0. Okay, so we have that, and we got to find the critical numbers for this. We're going to factor out a 4, it looks like. They all have a 4 in common, so this will be 3x squared minus, oh geez, 148, take a 4, 148 divided by 4 is 37. X, and then 336 divided by 4 is 84. And what I would do is, if you're having trouble factoring this, you could either do the quadratic, or you could just look for the x-intercepts of 3x squared minus 37x plus 84 on a graph, and that should get you kind of going. So you get 3x minus 28 and x minus 3. You would see that one of the x-intercepts happens at 3, and you could just use that to help you factor. Okay, or you could always do the quadratic. So we're going to get x equals 3, and we're going to get x equals 28 over 3. Okay. So I'm probably going to have to do a test on both of these. Okay. So I'm going to draw my number line. So remember, this right here was finding critical numbers. But a lot of times we have to go back and check if our numbers make sense to be called critical numbers. Remember, they have to be in the domain of the original problem. So the one that worries me a little bit is the 28 over 3, because 28 over 3 is worth how much? Isn't that about 9 and some change? That's about 9 1/3. So this guy worries me right here a little bit, 28 over 3, because remember, x is not the length of the rectangle, x is how much you're cutting out. Well, if that's a little over 9, and I try to cut that out from the 16, right? How's that going to work? How can I cut out a 9 here? Oops, sorry. How can I cut out a 9 here and a little over 9 here? Well, that would be 18. There's no way I could cut 18 inches from a 16-inch piece of cardboard. So 9 doesn't make sense with the problem. So we're going to get rid of that. So 9 1/3 doesn't make sense with the problem to be our cut. So that means the only thing we have to deal with as a critical number is 3. So remember, this is dv dx. Okay, the derivative of the volume with respect to x. So I'm going to pick a number to the left of 3, let's say 2. And when I plug 2 in there, I get a negative times a negative is a positive. So this becomes plus, 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 plus. Now when I plug a 4 in there, I get a positive and a negative. So that's going to be a negative, negative, negative. So that means we're going from increasing to decreasing, and that creates a maximum. Okay. Well, that's good, because what was the problem asking for? Maximum volume. So we know that x equals 3 is our max. Okay. This means we should cut out 3 by 3 squares from each corner to maximize volume. So this means that no matter how you cut this, no matter what you do, you cannot get a better or a higher volume than by cutting 3 by 3 squares out. If you cut a 2 by 2 or a 4 by 4 or 5 by 5, it will never produce more volume than the one we would produce by cutting out a 3. If they wanted to know the maximum volume, well, then we could just cut out 3 on each side, right? So this, we could say, well, this is 3, so this is 3, this is 3, this is 3, this is 3. Oops. This is 3, this is 3, this is 3, this is 3. So that's what we cut out. So that means that it would really be a 21 minus 6, so that'd be a 15 by a 10. So our max volume would be 10 by 15 by a height of 3. So that would be what? 450. And this would be inches cubed. Okay, so that would be our max volume if they asked for that. They just asked us to find the square, but in case there's a homework problem or something that has a follow-up, what would the maximum volume be? Well, now you know. Okay, so this will definitely let us get started on optimization. Okay, so I'm going to move forward. I think I have 1 or 2 more that I'd like to do for you, and that should cover all of optimization. Okay, so the next one says, so this is example what? Let's see here, where are we at? This is example 4. So example number 5. And as you can see, these all take a little bit of time. So on the exam, I couldn't give you like 20 of these. There'd probably be 2 questions from the exam from section 6. Or if there were 3, one of them from 4.7. If I were going to give you one, more than 2, I should say, one of them would probably be like a really easy one, like the first one we did. Okay, so it says a rectangle is inscribed inside of a semicircle radius 2. Okay. Oh, inside this of a radius 2 and the x-axis. So you use the x-axis as your border is what this is saying. X-axis. Okay. What is the largest area rectangle can have? Okay, so this is a classic problem. Okay. Example 5 now. Okay, so now we're on example 5. This is another good one. It says, so basically, let's draw a picture for this to kind of see. So take a minute, pause the video, and see if you guys can draw the same as me. Yeah, that's about as good as it's going to get. Okay, guys, so you guys are back. Let's take a look at inscribing this rectangle inside of my semicircle. Now, again, it's supposed to be symmetric. We know that this is -2 to 2, right? You know, I better use that. So this is -2, this is 2. Okay, and the vertex or the vertices made right here, let's name it x comma y. And again, I told you guys it's really important. When you say something's inscribed, it's going to touch it. So you should name that coordinate where they touch x comma y. It's very important to name things usually in math, especially in higher levels of math. Once you put a name to something, you can start working with it. So we inscribed our circle inside, we inscribed our rectangle inside of a semicircle of radius 2, and we use the x-axis. Okay, so this technically goes like that as well. Okay, now here's the thing. You have to bring a little previous knowledge for this problem. That's what makes this one a little bit harder. So it says a rectangle is inscribed in a semicircle of radius 2 and the x-axis. What is the largest area the rectangle can have? So we know that we're trying to maximize area. Okay, now let's look here. What's the height of this rectangle? Well, wouldn't the height be y? And what would the length be? How far is it from here to here? What's the length of this rectangle? Or I should say length times width, or base times height. Well, wouldn't the base be x? But it's not really x, because from here to here is x. But then how far is it from here to here? Isn't that also x? So that means it's 2x. So our area is actually 2x times a y. So we have an area formula that has two variables in it. And remember, the whole point is, I shouldn't say the whole point, but the reason you normally need two equations is because one of the equations is going to be used to rewrite the other equation with only one variable, the substitution method, right? So we need to come up with another equation, and this is what makes this problem harder. Remember, this is inscribed inside of a circle. So we could find this location here, and there's more than one way to do this. I've actually had a couple students do it a different way, and I didn't think of it that way, but it actually worked. But it also did sound a little bit complicated and hard to explain, but they were still able to do it, so it was okay for them. But when I teach it, I'd like to kind of go to a foundation idea that you should know about circles, okay? You guys know that a circle that is radius 2 means that you have x squared plus y squared is equal to 4. Remember, this is a circle centered at 0, 0, and it has a radius of 2. This is the base formula for a circle, right, of radius 2. So what I could do, and again, this is centered at 0, 0 right here. So what I could do, by the way, if you're wondering how did I know to draw the circle in this location, it's kind of, if you have to draw it somewhere, why not draw it around the origin? Kind of like, you know, we used to do with the unit circle. It doesn't have to be around the origin, but it just makes it easier for us. So that's why I chose to draw it there. And I chose to draw it on top instead of on the side or instead of on the left or the right, just so we could deal with positive stuff. I could solve for y, and I have y squared is equal to 4 minus x squared, right? And then I could square root both sides, and I would get y equals plus or minus the square root of 4 minus x squared. But I'm only going to use the plus because we're doing the top half of the circle. Technically, the negative would be the bottom half of the circle. So just keep that in mind. That's why I'm using the plus. So we have 4 minus x squared, okay, square rooted, okay? So that means we now know y. So we have our formula for area. Area is equal to 2x times y, but y is really the square root of 4 minus x squared, okay? Now, in general, what do we do next once we write our equation with one variable? In general, we dx it, or whatever variable we're working with. So I'm going to ddx this. So this would become dA dx, or a prime, is equal. Now, this one's a little bit harder. I have to do a little bit of work here because this is a product. So I'm going to do the derivative of the first, and then I'm going to rewrite the second, okay? Plus rewrite the first and the derivative of the second. So that might be a little bit more of a pain. That would be 1/2 times 4 minus x squared to the negative 1/2 times negative 2x. You know what? I'm going to run out of room, so let me rewrite this. Let me move this over here. So we have dA over dx is equal. And now we're going to do 2 times 4 minus x squared to the 1/2. So that's a rewrite of 4 minus x squared. Plus 2x times the derivative of 4 minus x squared to the 1/2, which would be 1/2 4 minus x squared to the negative 1/2. And then the chain rule says negative 2x gets attached. So this is starting to look like one of the problems from the exam 3 or exam 2 using chapter 3. Where you have to make common denominators with radicals. So let's take a look at that. So this is 2 4 minus x squared to the 1/2 plus, now these 2's cancel. Well, then I guess it's minus then, right? Minus 2x squared over 4 minus x squared to the positive 1/2 in the denominator now. Okay. So remember what I did then is I took and I wrote this over 1, and I gave this guy what it would need to be a common denominator, 4 minus x squared to the 1/2, 4 minus x squared to the 1/2, okay, because that's really just 1. So this is a technique that I taught you in chapter 3, that's why I taught it to you. So this becomes 2 times 4 minus x squared to the 1 now, right, minus 2x squared all over 4 minus x squared to the 1/2. Okay, so let's do some more. As you can tell, this one is definitely a step up in difficulty. So this would be 8 minus 2x squared minus 2x squared all over 4 minus x squared to the 1/2. And this is actually negative 4x squared plus 8 over 4 minus x squared to the 1/2. But this is actually negative 4 times x squared minus 2 all over 4 minus x squared to the 1/2. So this is our derivative now, right? We now have 4 times x squared minus 2. Now we have to find our critical numbers. So don't lose track of what you're trying to do. The whole point of all of this was to take the derivative so we could find the critical numbers. So I'm going to take x squared minus 2 and set it equal to 0. And I'm going to take 4 minus x squared and set it equal to 0. So this will be x equals plus or minus the square root of 2. And this will be 4 equals x squared. So then 2 plus or minus equals x. So we have our 4 possible critical numbers. But we have to be a little bit careful with this now, because some of these may not be acceptable. Some of these may not be acceptable in the domain, just like in all the previous problems. Okay, so I want to draw my sine chart, but I want to make sure that I'm not using a bunch of numbers that I can't even work with in the first place. So here's the thing. Could x ever actually be plus or minus 2? So let's go up to our picture. You're telling me that if x is 2, that means it would be right here. That's where you would put your rectangle. Well, how tall would it be if that's where it touches the circle? It would have a height of 0. So that doesn't even make sense, because obviously that wouldn't be the maximum height, because it would have, the maximum area, because it would have no area. So we're not going to do that. We're going to come back over to here, and we're going to cross out either one of these. Now, technically, plus and minus square root of 2, we're only going to do the plus square root of 2, because the negative square root of 2 would just be this guy over here. It would just be this one. And we only need to find one x. We don't need to find both, because they'll be the same thing because of symmetry. Okay? So I'm only going to test square root of 2. Okay? So I'm going to test a number to the left of square root of 2 on my dA dx. Okay? And I'm going to test a number to the right of my square root of 2, but it also can't be bigger than 2. So when I go and plug these in, when I plug a number to the left, and I'm assuming we can plug 1 in, so we'll get a negative here, a positive minus 2. So I'm going to say, let's plug in 1. I'll get negative something times negative 4. So that's a positive divided by a positive. So that would be a positive. And again, you guys can just use decimal approximations to plug in your calculator. Now I'm going to test to the right of square root of 2. So I'm going to use like 1.7 or something like that. And this would be a positive times a negative divided by a positive. So this will be a negative. So again, we're going from increasing to decreasing, and that creates a minimum. Okay. Now we were trying to find a rectangle. What is the largest area? Oh no, I'm sorry. This is not a minimum. If we're going from increasing to decreasing, we're creating a maximum, right? Sorry about that. So yeah, we're getting something like that. So that means that we have x equals square root of 2, okay? But the question says, what is the largest area the rectangle can have? So this is my correct answer for x, but that is not the largest area that the rectangle can have. So max area would equal, and I'm just going to use my formula, 2x times y. But notice this formula right here uses only x. So I'm just going to do 2x So this would be 2x times the square root of 4 minus x squared. And I'm going to plug in square root of 2. So this would be 2 square root of 2 times the square root of 4 minus 2, right? Because the square root of 2 squared is just 2. So this becomes 2 square roots of 2 times the square root of 2, which is actually just 2 times 2, which is actually just 4. So 4 units squared is our maximum area. So the maximum area our rectangle can have is 4. And this is actually a formula that you can kind of go through. What if it were a radius of 3? Then it would turn out that the maximum area was 9. You could go through and calculate this, so on and so on. But yeah, this would be one of the harder problems as well that you will encounter in your homework. Okay, and I just have one last one that I'm going to do, and this will be the end of the optimization. This is a rather long video, but optimization I normally cover in 2 days, so I'm just making like 2 half-hour videos, okay, in one. So we have this. Let's do, I believe this is example 6. Let's just double check. Yep, example number 6, and then we'll be done with this section. And again, you guys, this is a hard section, so don't feel bad. This is a rough one. Okay, if you're having a little bit of a hard time with this. Okay, so example 6. So it says a closed can needs to be made to hold 100 centimeters. Do something real quick, you guys. I'm sorry, I clicked a button accidentally. So it says a closed cylindrical can needs to be made to hold 1,000 centimeters cubed, okay, and of water, of H2O, okay. Find the dimensions R and H that minimize, oops. Oh my gosh. Surface area. Okay, so a closed cylindrical can needs to be made to hold 1,000 centimeters cubed of water. Find the dimensions R and H that minimize the surface area needed. So first thing, we need to know our volume formula because that is something they gave us. They told us that it can hold 1,000 cubic centimeters. So our volume formula for a cylinder is pi r squared times h, and that has to equal 1,000. Okay, this is a formula. Obviously, you guys will be taking the exam online for this because of the COVID-19 thing. So you will probably have this formula in front of you or in your notes or something, so that's fine. And then we need to know the surface area formula as well, because that's what we're trying to minimize. So just so you guys know, the surface area formula can be made from 2 circles and a right triangle, or I'm sorry, not a right triangle, 2 circles and a rectangle. If you cut the cylinder open, you would get a rectangle. So I'm just going to write the formula for you guys. If we were in class right now, I would show you with a piece of paper. You could fold up the piece of paper and then unfold it or roll it up, I should say, and you would get it. Okay, so that is the surface area formula. You know what, that's really ugly. Let me write that cleaner. 2 pi r squared plus 2 pi r h. Okay, so we need to do some work here. The problem is we have an r and an h, so we need to somehow solve for either r or we need to solve for h. So I'm going to look at this formula here, And it appears to me that it would be easier to solve for h. So I'm going to come over here and I'm going to say h equals 1,000 divided by pi r squared. Okay, I just divided the pi r squared over to the other side. So now that means in the surface area formula, I can get rid of h and replace it with 1,000 over pi r squared. So surface area equals, let's see here. Oh, and this is a cylinder, by the way. I should have probably drawn this. I just got carried away. Tend to do that sometimes. Okay, so we have our cylinder. We know this is the height. We know this is the radius, right? Okay, and we're trying to minimize surface area. So I'm going to do 2 pi r squared plus 2 pi times r times h, but h is 1,000 over pi r squared. Okay, so let's clean this up a little. Surface area equals 2 pi r squared plus, now one of these r's can cancel, okay, and then we'll be left with 2,000 pi, oh no, and the pi's cancel as well, sorry about that. 2,000 over r, I guess, oops, let me write it in black, over r. Okay, so let's take the derivative of this and we're going to ddr both sides. So now we'll have d surface area over dr is equal to 4 pi, because the derivative of 2 pi r squared is 4 pi r, plus, oops, it'll actually be minus 2,000 r to the negative 2, right? Because it's technically r to the negative 1. So now this is going to equal 4 pi r minus 2,000 over r squared. Now we have to make common denominators like we've been doing. So this needs an r squared and an r squared. So this will now become 4 pi r cubed minus 2,000 all over r squared. Okay, so now let me double check and make sure we're on the right path. So this is our first derivative. So now we're going to come over here. We're going to try to find our critical numbers. Okay, so our critical numbers for this will be, let's see here. Well, r squared, we don't have to worry. We don't have to worry about that because it could never be 0, because it doesn't make sense to have a radius of 0. So we're going to do 4 pi r cubed minus 2,000. And we're going to set that equal to 0, factor out a 4, and that will be pi r cubed minus 500 equals 0. So now we're just going to take pi r cubed equals 500, divide both sides by pi, and we have r cubed equals 500 over pi. Okay, so then you cube root both sides. This isn't pretty, but we have r is equal to the cube root of 500 over pi. Okay, so this is our critical number we're going to use, the cube root of 500 over pi. Okay, so we're going to test to the left and we're going to test to the right. Let's see here, I'm running out of steam a little bit. So we're trying to minimize. If you find out the cube root, so I'm going to do 500 divided by pi, and I'm going to take that to the cube root. I get about 5.4-ish. So I'm going to pick a number around 4. When I plug that in, I'm going to get a negative. And then when I plug in a number around 7, I'm going to get a positive. And I'm just picking numbers to the left and the right. So that means we're going from decreasing to increasing. And if we go from decreasing to increasing, we're getting a minimum, and they were asking us to minimize the surface area. So this is my R value. Now, again, if I want to find my H, remember we said that H was worth 1,000 divided by pi r squared. So I got to come over here. H is worth 1,000 divided by pi times r squared. But we know that R, 1,000, we know that R is worth the cube root of 500 pi. So this would be pi times the cube root of 500 over pi. And then this is all squared. Okay. When you guys clean this up, the ugly version of this is going to be 10 times 2 to the 2/3 all over pi to the 1/3. But I would allow you to leave this as well. So these are our dimensions of R and H that would minimize surface area. Okay. Any questions about this? Okay, be sure to ask me in the next meeting we have. This one is a hard one, but more because the answer is ugly. I would say the work in this one was easier than the derivative in this one. This derivative is much harder. So make sure you guys are going over the video, pausing the video to see if you can do it yourself. Okay, when you're doing it without my help, and then turn on the video to get it done. But I'm going to end the video now for chapter 4.7, optimization. Hope this helps you guys get started on the homework.